Okay, so we are doing two sections today. So we're doing 3.1, which is quadratic functions. And like I said, this should be review, but it's going to be going back and forth between vertex and standard form. And just to let you know, this textbook is kind of weird. It actually, standard form, and I'll go through what standard form in it, you can see it down at the bottom there. But what a lot of books, what most teachers, what most people call vertex form, this textbook actually calls standard form. Um, CPM, I think, called it graphing form. There's all these different names. And then there's standard form, which a lot of people think of as the ax squared plus bx plus c, but this textbook calls it general form. Honestly, I don't care what you call it, but the reason why I'm making a point about this is when you're doing your homework tonight, you're going to see some sections like talk about changing the equation to standard form, or use standard form to graph blah blah blah. When they say standard form, they're actually talking vertex form or graphing form. So that's the reason I'm making a big deal out of that, just so you know what to do on your homework. So, but we're going to do that. We're going to look at how you graph using vertex and intercepts, and also how you write the equation. So that's going to be review, but then we're going to go into polynomial functions, and that's the main focus for this entire unit. So today we're going to focus on just some basic parts of graphing, because our goal at the end is to be able to graph these polynomial functions. And the thing is, polynomial functions have all different shapes to them. So how do you do it when there's so many different shapes? So we're going to look at a good way to be able to do it with just some minimal knowledge. And that today we're going to focus on something called the leading coefficient test, which helps us find end behavior, and then how we can look at zeros and their multiplicities, whatever that means, to help us. So that's the focus. So let's first talk about quadratic functions. So we have standard form, and like I said, the book calls this general form, and it's this form. It's the y equals ax squared plus bx plus c. If a is positive, remember it opens up, and if a is negative, it opens down. We know that. And then vertex form, and like I said, I believe, but I can't remember. I actually never taught IM2 out of the CPM books, but I believe CPM calls it graphing form. But this textbook calls it standard form, and this is the y equals a times x minus h squared plus k. And remember, this is vertex form because the vertex is right there. hk is your vertex, but again, a opens up or opens down depending if it's positive or negative. And this a, by the way, is the same value as this a. So when you're changing back and forth between the forms, this a will always be the same. So, okay. So for the rest of the notes, I'm going to use the book's vocabulary. So I'll be calling vertex form standard form. Just try to get used to it. So when you're doing your homework, it won't be so jarring. So let's look at how we convert. And by the way, since I know I did say that I'm not going to slow down to let you guys write, but please stop me if you have questions. I have the chat right next to the screen right here in front of me. So feel free to put things in the chat if you have any questions. Okay, so how do you convert from standard to general form? So here's standard form, and we want to go to this form. This is actually the easy one. You just work it out. So you do your order of operations. So we're going to do exponents first. So we do x minus 7 squared. And when you do that, you're going to get x squared minus 14x plus 49. But then we still have to multiply that by the negative 2. So I distributed it, and then you add 3. So there's really nothing to that. That's really super easy. So any questions about this right here? Okay, so now converting from general to standard form, that takes a little bit more. That's using completing the square. So let's see how we do that. And I'll actually, now that I think about it, I'm going to go ahead and put a little description next to this stuff here. So we start with this. This is our general form. And we want to go to something like this where we can see the vertex in there. And notice it didn't take too many steps. It's not too bad. So what you have to do, though, is we're going to complete the square on the term, or on the variable that's squared. So since x is the variable that's squared, I'm going to just collect the terms with the x's on one side, and I moved this 1 over to the other side. So we're going to separate the terms with an x. So that's what I did right there. Now completing the square, that process of completing the square only works when your coefficient of x squared is 1. And right now the coefficient of x squared is 2. So if you ever have something other than a 1 in front of x squared, you have to factor it out. So we're going to, that's our a value. So I'm going to say factor out a if a doesn't equal 1. So a was equal to 2, so I had to factor it out. Oh no, I didn't factor it out. Look at that. We're going to change all of this. Hopefully I can work it all out there. Another silly mistake. Okay, so I factor out the 2 and I get this. So now let's see what happens, how this is going to change everything. So now we're going to complete the square. I'm going to just abbreviate complete the square with CTS. CTS is complete the square. And remember what you do with that is you take half of b, so we're going to divide b by 2, and you square it. So for this one, b is a negative 4. So if I take half of negative 4, I get negative 2. And negative 2 squared is positive 4. And that's actually going to change all of this stuff too. Okay, so, but remember, whatever you do to one side, you do have to do to the other. So if I added a 4 onto this side, I have to add something onto this side too. Does anybody know, since we're working this one out together now, does anybody know what we're going to have to add to this side to keep the equation balanced? Oh, good. I see a lot of it. Yeah, we're going to have to add an 8, which is weird. And if you don't see it, the reason is we're not really adding a 4 here. We're adding a 2 times 4 to the right-hand side. So that's one thing. Watch out for that silly mistake, which, hey, we all make silly mistakes, as you see. So, so that's why we had to add an 8. Are there any questions why this is an 8 and not a 4 here? Okay, so then it's going to be a matter of simplifying the left, simplify left side, factor the right side. So what do I mean by that? Well, we have a negative 1 plus 8 there. That's going to be plus 7. And then on the right-hand side, we can factor that, quadratic, and it's going to factor into x minus 2 squared. By completing the square, the reason why we call that completing the square is you're always going to be able to factor this into something squared. It's always going to work. So so that's what we did. And it's always, what's cool is it's always going to follow the same pattern too. Just take half of b, which is negative 2, and that's what's going to go there. And then once we do that, then the nice thing is we just have to add 7 onto the other side. So I'm going to just go ahead and bring all that. And so we're going to want to cancel out that positive 7 and make it a negative 7 over on this side. And now we have our standard form. So just solve for y. So sorry about that little mistake there in the beginning, but any questions there, how that works? Okay, so now how can we use these different forms? And we have these different forms because it just kind of depends on the numbers and depends on what we're doing with it. Sometimes standard form is nicer, sometimes general form is nicer. So now let's get into the graphs. Oh, here's another completing the square one, just so you can see first of all. So let's see if I made a mistake on this one. So we started off with this. So remember, the first thing is I got to move that 7 over to this side, so it becomes a positive 7. A does not equal 1, so I had to factor it out, and this time I did remember to factor it out. And then we have to complete the square. So half of negative 2 is negative 1, but negative 1 squared is positive 1. So that's why there's a 1 here, but I really added a negative 3 times 1 to the right-hand side, so that's why there's a negative 3 there. And then I combined my like terms and factored this, and then just moved the 4 over. So fairly friendly. So any questions? Okay, so then how do we graph? And there's different methods depending on what you're dealing with. So let's see, graph using the vertex and intercepts. So what if I want to graph this one right here? So one thing that I can do is I can find an equation for the line of symmetry. Because remember, our parabolas, there's always that line that cuts it in half, and the vertex is always on that line of symmetry. Your line of symmetry always has this equation, negative b over 2a. So we're going to use that equation there, and so I go ahead and do it, and I get x equals 1/4. That is also my x-coordinate for the vertex. So now I know the x-coordinate. Now it's going to be a little messy because we have a fraction, but that's okay, we can still deal with it. Once I know the x-coordinate, all I have to do is plug into this original equation to find the y-coordinate. And I guess I'll put this up here. So that's what I did. I went ahead and took that original equation, but let all the x's equal a 1/4, and then I started working it out. A little trick here, if you keep this in mind, you're doing 4 times 1/4 times 1/4. Remember, 4 times 1/4 is just 1, but then you have another 1/4. That's how I knew that was 1/4. And 2 times 1/4 is 1/2. Then I changed everything to have a denominator of 4, and I got my y-coordinate. So there's my vertex. So I had to do a little bit of work. And then to find the x-intercepts, you let y equal 0. That's how you always do it, no matter what kind of equation it is. Anytime you want x-intercepts, you let y equal 0. So I let y equal 0, and then I tried to factor this thing. First, everything divided by 2, so I divided both sides by 2. And then this does factor, and set each factor equal to 0, and you get your x-intercepts. And then the y-intercept is nice. You let x equal 0. It's always going to be that constant term at the end. So I know I went through all those things kind of quickly, but any questions over what I was doing there? Because the point is, now I have the vertex and I have some other points on the graph. I'll be able to get a pretty accurate graph from this. All right, I don't see any questions. So then you would, oh yeah. Are you talking about this right here? Oh, yeah. So over here, so I'm not dividing by a form of 0. So that would be one thing to watch out for. If I'm dividing by 2, I'm dividing by 2. And then I just did it. 0 divided by 2 is 0. And all of this divided by 2 is that. So yeah, as long as it's an equation, I am allowed to divide both sides by a constant other than 0. All right, any other questions? Okay, now I graph it later on, but I'm going to do, remember this was one method, which was using the line of symmetry to find the vertex. But another method is to rewrite in standard form, doing that completing the square. And so that's what I did here. And you see when there's fractions involved, it gets a little messier, but the process is exactly what we were doing above. So here's my original equation. So I still want to separate the variables, the x terms, from everything else, so I added 6 onto both sides. A was not equal to 1, so I had to factor out a, so there's the 4. And then you can see that this is where fractions are going to come in, because when I factor out a 4 from 2, I'm going to get 1/2. But that's okay. And I know a lot of people are tempted to change things to decimals, thinking, oh, decimals are so much easier. But actually, if you're working without a calculator, most of the time fractions are easier. Just get comfortable with them. The only way you're going to, get comfortable with fractions is if you force yourself to deal with them. Once you get comfortable, they're actually usually much easier to deal with than decimals. So for completing the square, half of 1/2 is 1/4. And then if I square 1/4, that's 1/16. Much easier to do than half of a half is 0.25, and then 0.25 times 0.25. Well, maybe you know 25 times 25 is 625. So it'd be 0.0625. Be really easy to get off in decimals. Deal with fractions. So much better. But I added 1/16 here, but it's really 4 times 1/16. So that's why I added 1/4 here. And then combine these to 25/4. Factor this. And remember that trick for factoring. As long as you completed the square correctly, it's always going to factor into, this thing is always going to be half of b. So half of 1/2 is 1/4. And then just put the 25/4 over here. And now we can see our vertex, which is the exact same thing that we got up above on the previous form. Which one's easier? I don't know. I mean, both ways you got to deal with fractions. Just kind of a personal preference, I think. And then you would find the x-intercepts and the y-intercepts exactly like we did above, so I didn't work those out again. It's really just finding the vertex, two different ways to do it. But then once we know the vertex, I plotted that point. I plotted these three intercepts. Notice my scale, by the way. I used 2 squares on the x-axis to be 1, but then only 1 square on the y-axis. By default, like if you don't label your axes, it's assumed you're counting by ones. But if you change anything, like I changed this, I've got to label it. So, but then I just plotted those points and graphed the parabola. So any questions about that? All right, so then writing the equation from points on the graph, and it just kind of depends on what you're given. So here's one example. The key is here we're given a vertex. If we're given a vertex, let's use that form that has the vertex in it. So right away I can plug in the 2, 2 into h and k. And then to find a, I can use this other point. That's an x and a y coordinate. So I can let x equal 3 and y equal -1. And just work it all out. Once I fill in for x here, that's 3 minus 2 is 1. 1 squared is 1, so I have 1a plus 2. But then subtract 2, I get my value of a, and voila. So not too bad as long as you remember these forms. So any questions on this one? Oh, sorry, I saw a question before. I'll get back to that question. Sorry, the one in the chat. I'll get back to it. Any questions on this one? Okay, so then while we're on this idea of writing the equation from the graph, then the other kind of thing, what if you're not given the vertex? And I didn't actually label these points, but I'll label them. So this point is 5, 3, and this point was -1, 0, and this point is 4, 0. So this time we have x-intercepts. So if we have x-intercepts, that means that they came from these factors. If -1 is an x-intercept, that means the factor it came from was x plus 1. And if 4 was an x-intercept, that means the factor it came from was x minus 4. So these were factors. There was just some mysterious value of a that we still don't know. It's always, at the end, you're always trying to find a. So we're going to do exactly what we did on that previous problem. We have one more point we can use. And so I plugged in x was 5 and y was 3. So these x's became a 5. This y became a 3. And then just worked it out to get a is 1/2. So there's my equation. And pay attention to the directions. If the directions don't tell you what form to leave your answer in, leave your answer in whatever form you want. I'm going to leave my answer in this form because there were nothing in the directions that said leave it in vertex form or leave it in general form, so I'm just going to leave it there. Same thing on this one. It made more sense for me to leave it like that because the directions didn't tell me. So as long as the directions don't tell you what form to leave it in, it's your choice. You get to leave it in whatever form you want. So any questions on that before I go back and answer the question in the chat? And then that's going to be quadratics. Okay, so the question in the chat was about finding the x and y intercepts. So let's see, there it is. this problem, because I didn't work it out. Remember, since this was the same equation as the previous work, 4x squared minus 2x minus 6, 4x squared minus 2x minus 6, I had already worked out the x and the y-intercepts here. That's why I didn't show it again. But in general, remember, you let to find the x-intercepts, you let y equal 0. So in this case, it was easy to solve this quadratic by factoring. You could always use quadratic formula if factoring doesn't work. And then to find the y-intercept, you always let x equal 0. So I just took this equation and let the x's equal 0. So any other questions on quadratics? Okay. All right, I know that was a lot fast, but like I said, hopefully that was review for you. But let's look at polynomials now. Polynomials of a higher degree. Okay, so first of all, what is a polynomial? Just so we make sure we're clear on that. And this is a formal definition for what a polynomial is. But what this is all saying, oh my God, there's so much. So let's look, n is a positive integer. N is in the exponents. So it's saying that our exponents have to be whole numbers. I do have an exponent here of 0. So it looks like exponents can be positive, whole numbers, or 0. And these a sub i's, these are all coefficients. So your coefficients have to be real. So coefficients have to be real. Your exponents on your variable can't be negative, and they have to be whole numbers. So for instance, all of this, all the coefficients are real. All of the exponents on the variable, they're all whole numbers and nothing's negative. Same thing here. Even 5 is considered a polynomial. It still follows this form. Not a polynomial. We have a coefficient of I here. That is not real. It is not a polynomial. We have a negative exponent on the variable. Not a polynomial. That's not even a whole number. The square root of 2? That's not a whole number. That's like 1.414 blah blah blah. So not a polynomial. These exponents are fractions. Not a polynomial. When you do have polynomials, we can talk about the degree. The degree is the biggest exponent on the variable. So the biggest exponent was 4. Here the biggest exponent is 1. On this guy right here, the 5, it's like there's an invisible x to the power of 0. So we call it, whenever you have a constant, it's degree 0. And there's only one exponent here, so it's 5. So just to get some vocabulary down so that we can use that vocabulary later on. Any questions at all here? Okay. So like I had said in the beginning, actually before I scroll on, we're going to look at how to do graphs. Actually, I'll do this. And these are graphs of polynomials. Graphs of polynomials are always continuous, smooth curves. You can't have any sharp corners, like an absolute value, has a sharp corner on it. It's all just continuous, smooth curves, which is really nice. And then the ends of the graph, and that's what we call our end behavior. What is the graph doing at the end? Well, the curve is either going to approach positive or negative infinity. Positive infinity means the graph is going up. Negative infinity means the graph is going down. So you can see on this first one, on the left it's going down, and on the right it's going down. So on the left, we're going to negative infinity. On the right, we're going to negative infinity. But it's just doing these up and downs in between. Same thing here. We're just doing some up and downs in between, but on the left it's going to negative infinity, on the right to positive infinity. You can have some cool little squiggles like this. On the left it's going to negative infinity, on the right it's positive infinity, but it's doing some squiggles in the middle. So polynomial graphs can all look so different from each other. So how do we have a nice method for being able to determine what the graph is going to look like without using a calculator? And that's where, today we're just going to focus on two things. Today we're going to focus on how do you find this end behavior? How do you know if it's going down, down, or down, up, or even up, down, or up, up at the ends? And the other thing is, when it crosses the x-axis, how is it crossing? Is it just going right through when we have zeros? Is it doing something like this, where it kind of just flattens out for a brief moment and then comes back up? We call this terracing. Or maybe it bounces at the x-axis. So how can we determine all of that when every polynomial is so different? And so that's what we're going to focus on today. So any questions about that? Okay, it's actually pretty easy, believe it or not. So I kind of talk about that. So let's look at the end behavior. So there's something called the leading coefficient test, which I always find weird because we also have to look at the exponent, not just the coefficient. I don't know why they don't call it the leading term test, but whatever. So we look at the leading coefficient. So here's our polynomial again, remember? The biggest exponent is your degree. So n is called the degree. And then the coefficient in front of that is called the leading coefficient. So here's a little table of this is something to memorize, but I'll give you a quick way to memorize it. So let's first look at what this table is saying, because it looks a little confusing at first. It's not so bad. So if we look at it, just kind of focus on the pink, focus on the picture part. Your leading coefficient, it's going to be positive or negative. And your degree is either even or odd. So based on that, we can determine the end behavior. And it's easy to remember. Forget about the blue and the green stuff in here. Just look at the pink. It's actually really easy to remember these because there's two kinds of graphs that you guys know really well. You know lines and you know quadratics. And here's all you need to know about those. So a line, actually I'll put it over here. Think about a line. Y equals mx plus b. What is the degree of a line? Very good. It is degree 1. The biggest exponent on the variable is a 1. So if it's degree 1, it's an odd degree. M is your leading coefficient, and M represents the slope. So, and you guys know positive and negative slopes. So if it's odd degree, think about a line. Think about a line with a positive slope, and that's a line that goes uphill. It's down on the left and up on the right. Down on the left, up on the right. That's your end behavior. If you have a line with a negative slope, you know it's going downhill like that, which means it's up on the left, going up, and it's down on the right. Oh, wait a minute, I put that in the wrong spot. My bad. Pay attention. Right here. Sorry, if it's an odd degree, so line with a negative slope, think about a downhill line. So up on the left, down on the right. So that's something you guys know. So that makes it a little easier to memorize. So this part right here, you can just use that. Then, for an even degree, you guys know about quadratics. And so I'll put over here y equals ax squared plus bx plus c. The degree is 2. It's an even degree. And your leading coefficient is a. And you know when a is positive, it's going to open up. So you have a parabola that looks like that. It's a smiley face. So it's up, up on both ends. And then if it's got a negative leading coefficient, it looks like a frowny face, it opens down. So it's down, down on both ends. So it's an easy way to memorize this table. So although I say you have to memorize it and it looks really complicated, it's not as bad as it looks because you guys already know lines and quadratics really well. So again, forget about the blue stuff. I haven't explained that. But any questions on the pink and the green now? Okay. So then there's just some fancy way we can say, normally mathematicians were very efficient. This may be one of those times you can say that we're being less efficient in our language. But this stuff in blue, it's a fancy way of saying the green stuff. And I want you to start getting used to it because it'll help you when you get into calculus. Because calculus will use this kind of notation a whole lot. So this is just to give you a taste of it, to help you get ready. It's good to be able to read it. I won't require that you write your answers using this blue notation, but I may describe things. Like, so if I'm going to give you a test of some sort, I may, in the directions for the problem, use this blue language. But if you have to write your answer, it's okay if you use the green language. So how does this blue language equal the green language? Well, as x approaches negative infinity, your x-axis goes left and right, If x is going to negative infinity, that means it's going left on the x-axis. And so that's why x is approaching negative infinity means left. If x is going to positive infinity, this little arrow you read as approaches. So as x approaches positive infinity, we're moving to the right. And then f of x is the same thing as y. The y-axis goes up and down. So if I'm going to positive infinity, that means I'm going up. So f of x approaching positive infinity is up. F of x approaching negative infinity means down. And that's how you read all this blue stuff. So any questions about that? All right. So it makes leading coefficient and finding end behavior sound really complicated, but it really isn't. When we get to doing examples, you're going to see it's not that bad. It's really just going back and thinking about lines and quadratics. Is it an odd degree? Think about a line. Think about a line with a positive or a negative slope to see what it's doing on the ends. Is it an even degree? Think about a quadratic. Think about a parabola. Is the leading coefficient positive? Then it's going to be up on both ends. If the leading coefficient is negative, it's down on both ends. But I'm going to wait to do some examples because I want to show you about the zeros and then we're going to put it all together. So any questions on this table? Okay. So then let's look at zeros. So zeros are the same thing as the x-intercepts. So that's what we're finding really, is the x-intercepts. So you guys already know how to find zeros. We haven't talked about multiplicities yet, but they're super easy also, especially when it's in factored form. So the multiplicity refers to the number of factors that the zero comes from. So like right here in this example, x minus 3 is squared. That means there's 2 factors that are x minus 3. That means that x equals 3 has a multiplicity of 2. And then we have x plus 5, which gives us x equals negative 5. It only appeared one time. It has a multiplicity of 1. And this guy, he's got a multiplicity of 3 because there's 3 factors that give us that. That's all multiplicities are. This quadratic doesn't factor, so if we try doing the quadratic formula, we can still find zeros. Notice this was not imaginary. A lot of students get mixed up with that and they go, oh, it doesn't factor, there's no zeros. Not necessarily. If it doesn't factor, you still need to see if there are real solutions. And this one, there are real solutions, so we still have 2 other zeros. They're just a little uglier. So remember, the 3 had a multiplicity of 2, and so we indicate that with a little subscript in parentheses. Negative 7 had a multiplicity of 3, so there's that. If it has a multiplicity of 1, it's implied it's 1. You don't have to put a little subscript of 1. And then these also only had a multiplicity of 1. So that's how you find multiplicities. Any questions how you find them? How you find zeros and their multiplicities? Okay, so what do we do with that? Well, the multiplicity can tell us how the graph is going to cross the x-axis. If the multiplicity is 1, that's when it just goes straight through, it doesn't do anything special. If the multiplicity is odd, greater than 1, that means it terraces. That's when it flattens out. So just for one brief moment in time, the graph flattens, and then it continues up. Some people have trouble drawing terraces. Here's a way you can think about drawing a terrace. Let's say you've plotted your 0 on your x-axis. Think about drawing half of a parabola. Draw half of a parabola, but then stop. And then on the other side of the x-axis, draw the other half of the parabola. I see all sorts of crazy things with terraces. Terraces flatten out, like I said. Some people try to do like this. That is not a terrace. That's not flattening out. That's going vertical for a brief moment. It's got to flatten out. So it's got to flatten out and then go up. And then some people will draw a terrace, but like terrace above the x-axis. That doesn't work either. Here's the part where it's flattening out, but that's not on the x-axis, so that's not a 0. So like I said, if you have trouble drawing terraces, which is fine, I mean, it's no big deal, but the way to do it is thinking about a parabola. And just think, whichever direction you're coming from. Draw half of a parabola on one side of the x-axis, half a parabola on the other side, and you got a terrace. And if the multiplicity is even, then we say the graph bounces at the x-axis. So it just gives it a little kiss and then runs away. So now that we know end behavior and we know about multiplicities, we can actually come up with a graph pretty decently. So now I just got some examples with graphs and then we'll finally be done. I know, this is riveting, isn't it? Any questions so far? Okay, so putting it all together, how can we use end behavior and the multiplicity of the zeros to help us graph? So here's one example. It's all factored out though, which is going to be helpful with the zeros, but for the leading coefficient, like we have to multiply all this together to find the leading coefficient and the degree. Or do we? We don't actually have to multiply it all together, but we have to think about what it would look like if we multiplied it all together. But remember, we only care about that first term. To find the leading term, just think about the first term. So here was the problem. I just copied the problem down here. And just look at the leading term in each one of these factors. So I have the -2, and then I have an x, and then this x was squared, so I have x squared, and then this x was cubed, so I have x cubed, and then there's going to be some other stuff after it, but I don't care about that. What happens when you multiply all this together? Well, add your exponents. You're going to get -2x to the 6th, and some other stuff that we don't care about. So if it's in factored form, it's actually not that big a deal to find the leading term. So any questions how I got that? Okay, so now we have to think about the end behavior. The degree is even, so we're going to think about a parabola. The leading coefficient is negative, so we're going to think about a parabola that opens down. That means it's down on the left and down on the right. So now we know the end behavior. And then I use that fancy notation. As x approaches -infinity, as it's going to the left, f of x is approaching -infinity. It's going down. As x is approaching positive infinity, going to the right, f of x is approaching -infinity. It's going down. So there we go. That's how I find end behavior. So any questions about that? All right. Now let's look at the zeros. So I just rewrote the problem here so we could have it as a reference, but since it's in factored form, we don't have to do any work to find the zeros. We can see that x equals 3, x equals -4 with a multiplicity of 2, and x equals 5 with a multiplicity of 3 are the zeros. No work there. And because that's even, we know it's going to bounce. And because that's odd, bigger than 1, we're going to have a terrace right there. So any questions how I found the zeros and their multiplicities? I'll show you the next example as if it's not factored. So I'll show you what that looks like. Sorry, I should be paying more attention to the chat. I didn't pay attention to there's a question about multiplicity is, multiplicity, remember, is just based on how many factors the zero comes from. You can just look at the exponent. So the exponent here is 2, so that's why a multiplicity of 2. And then this exponent was 3, and that's why a multiplicity of 3. And so then we graph. Woo! So I like to actually plan out the graph. So the way I do it is, first of all, I graph it, set up my axes, and I mark my x-intercepts. And sometimes, especially if you have a lot of x-intercepts, and sometimes it's going to bounce, and sometimes it's going to terrace, sometimes it's going to go straight through, and trying to remember as you're graphing what to do at each one. You can do whatever you want. You can put whatever symbols you want. I put a little tiny arrow where it's going to bounce, and I put a little tiny squiggly arrow where it's going to terrace. And that just reminds me, bounce here, terrace there. You can do whatever you want to help you out. And then remember the end behavior was down, down. It was down on both ends. So I kind of first thought about, okay, if I'm going to start here, I'm going to come up here, I'm going to bounce. And then I come down. Now the one thing I don't really know how low to make this. I don't know if it is go way down. Maybe it just is more up here. I don't know where this turning point is. And that's something we're not going to be able to figure out this year. Next year in calculus, that's when you figure it out. So for now, turn around wherever you want. So I'm going to bounce. I got to turn around some point to go back to this x-intercept, and I just go straight through. And again, I don't know where this turning point is. That turning point could have been really high. The graph might have gotten super steep. I don't know. But then I have to terrace here. Oh, and then I end down, so that looks good. I was supposed to end down, and I did. So that's a nice way to check yourself. So I kind of think about it a few times first before I actually graph it. But all of these points where we turn around, where we change direction, we're going up, and then we turn around to go down, and then we turn around to go up, and then we turn around to go down. These are called turning points. If the turning point happens to be a bounce at the x-axis, of course we know where that is. We will not be able to find these turning points. The book actually wants you to plug in values of x to determine where the turning point is, which I think is the stupidest thing. Because if you're going to do that, you're going to use a calculator. And if you're going to use a calculator, why not use the calculator to graph the polynomial in the first place? I do not want you plugging in random values of x. That is the silliest and most inefficient thing to do. So for us right now, you're going to turn around wherever you want. Now, because of that, I actually, on polynomials, I'm not going to focus on this y-intercept. It'd be really easy to find the value of the y-intercept, because all we'd have to do is let all these x's equal 0 and work it out. But I don't want you guys to do that, because that I think is a waste of time. And then also, that makes us have to put a scale on the y-axis, and we don't know where these turning points are, which may not line up on the right place of the y-axis. So notice I didn't even put any kind of scale on my y-axis. I don't care about that for polynomials. It's all about the x-axis. But we knew the end behavior and we knew the behavior of the zeros, and there's our graph. So any questions how I got that graph? Which, by the way, I did go ahead and graphed it on Desmos. This is how the graph actually looks. Now you can see our general shape is there. We have a bounce, we're going straight through, we have a terrace, and the end behavior was down, down. End behavior is down, down, and we have a bounce. It's going straight through and terrace. We just have a little tiny tip here because our y-intercept was so far down on the y-axis. But for just a little minimal amount of work, I think we got a pretty decent graph. So So remember, you know if it's going to bounce or terrace based on the multiplicity. Even bounces or even multiplicities bounce. Odd multiplicities bigger than 1 terrace. So it's all about that. And there's another question about explaining briefly. I'll do that on the next one because we have just one more example, and hopefully that'll be another way to see it again. Any other questions on this one? Okay, so our last example then, sorry, 2 examples, but they're going to be pretty straightforward. Oh, I don't want you to see that. Try these on your own, actually. So here's one to try. And just find the end behavior and the multiplicities, and then see if you can come up with a graph. Here's one that's not factored. If it's not factored, you're going to have to factor it first. But this is one, oh my goodness, if I write that correctly. That should be an x squared. There we go. So this should be one that you can factor. So give those a shot. I'm only going to give you about 5 minutes. I'm going to pause right now the recording. All right, so let's take a look. Let's see the first one. So the first one's already factored. So we have to find the leading term to see the end behavior. So I can't quite bring it up all the way. So remember, just think about multiplying all of the leading stuff in each factor. So we do have the negative 1/10, and then we have the x cubed, and then I have a 2x, and then I have x to the 5th. And then there's going to be other stuff that I don't care about. So if I multiply all that together, it's going to be negative 1/5 x to the 9th. The degree is odd, so I'm going to think about a line with a negative slope. So that's going to go downhill, which means it's going to be up on the left and down on the right. So any questions on end behavior? All right. So then we do the x-intercepts, and because it was already factored, those were nice. We have x equals 1 with a multiplicity of 3. We have x equals negative 3/2 with a multiplicity of 1, and x equals 4 with a multiplicity of 5. So we have 2 odd multiplicities greater than 1. That means we have 2 places where it's going to terrace, and 1 place where it'll go straight through. So any questions how I got this part, the zeros and what it's going to look like? All right, so then your graph should look something like this. So negative 3/2 is right there, but it doesn't do anything special. But it does terrace at x equals 1 and x equals 4. And then remember, it's up on the left and down on the right. So I have to start from up here, go straight through, turn around somewhere, I don't know where, flatten out for a brief moment, flatten out for a brief moment, and continue down. So any questions at all how I got this one? So remember, I'm not going to worry about how high or low these turning points are. Okay. Then the last one. So it's already multiplied out, so we can find the end behavior right away. A positive leading coefficient with an odd degree is like a line with a positive slope. So it's going to be down on the left and up on the right. But I do have to factor to find the zeros. There is a common factor of x, and then it's a quadratic that factors into this. So I know I have a 0 at 0 with a multiplicity of 1, and then a 0 at 5 with a multiplicity of 2. So it's going to bounce here. So then putting the end behavior of down, up, along with the zeros, I wind up with something like that. So any questions over anything? Because that's, finally made it to the end. It seems like a lot, but it really isn't. It's just, I mean, the new thing was really end behavior and zeros and multiplicities.